Hi and welcome to Year 11 Maths and the class on gradient from exercise 7.3. So if you can recall back to Year 9 and Year 10, we spent a lot of time talking about gradient and we came up with a whole lot of different ways we could describe gradient, and one of those was slope. Gradient and slope are effectively the same thing. And you may or may not remember I talked about how the slope or the gradient was a numerical value. It was a number that was able to tell us how steep a line is. Well, there were 6 ways that we've actually used in the past, or 6 different ways that we've described gradient in the past. Can you remember what any of them are? Well, I've got 3 of them in bold at the top of the screen already. Gradient, slope, steepness. What were some other ways that we described this concept? Well, one of them we used was lowercase m, small letter m. And we know that m was a way of describing the gradient, or the slope, or the steepness of a line. We also knew from year 9, or know from year 9, that rise over run was another way that we could describe slope, and y2 take y1 on x2 take x1, which was another formula that we used to find slope when we were given 2 points. Well, what do we remember about gradients? If a line had a gradient of 0, that means that the line was horizontal. It had no steepness, it was flat. If the gradient was 1, you might remember that a positive number means that the line went uphill if we looked at it from left to right across the page. And a gradient of 1 would actually go uphill at a 45-degree angle. We don't need to know where the 45-degree angle comes from at the moment. We'll look at that a little bit later. A gradient of 5 is a bigger positive number, so it's actually still going to go uphill from left to right, but at a bigger angle. And a gradient of 5 would be about a 79-degree angle uphill from left to right. If the gradient was negative, you might remember that that meant we were going downhill as we look at the line from left to right. So gradient of minus 2.5, well, that's going downhill at about 68 degrees. And there's all sorts of ways we can consider it, but we're actually focusing on the angles a little bit towards the later. We're focusing on angles in this exercise, so that's why we want to introduce this concept now. Now, if we consider a line that goes uphill from left to right. Now, if I look at this line, I'm going to have 2 dots, one at the beginning and another one at the end. So the one at the beginning is my first dot, the one on the left-hand side of those 2 dots. From that dot, I could go horizontally, across, and then vertically up. And you might remember that that's actually what we call our run and our rise. The horizontal distance is the run, and the rise goes up, just like a sunrise goes up into the sky. The rise is up, and when you like to run, you run horizontally along the ground, so our run is along the ground. But from that little dot over on the far left-hand side, I didn't have to do the run first, followed by the rise. I could have risen up first, and then had a little bit of a run. And when you actually start to look at that a little bit more carefully, you'll realise that it doesn't matter whether you go running first or running second, those distances are both the same distances. And when you look at the rise, doesn't matter whether you did it first or second, those rises are the same distances. So effectively, it doesn't matter which direction you go first. What about if you go downhill from left to right? Well, again, let's consider the beginning and ending point of my line. There's 2 little dots there. Let's go to the one on the left, the left-hand part of the line. We can choose to go downwards. So that rise is actually negative because we're heading downwards. Upwards is a positive direction. Think of a y-axis on a graph. If you're heading upwards, you're heading in the positive direction. If you're heading downwards, you're heading in the negative direction. Followed by a run, that is positive because the run is heading in the positive x direction. If you were thinking of the run as a horizontal line, the x direction to the right would be positive, to the left would be negative. Alternatively, we could have gone and done our run first, which is still positive because it's to the right, or we could have done our rise second, which is still downhill, so it's still a negative value, which means when we look at these two different scenarios, what we actually have is when we look at the first line, the rise and the run are both positive, and a positive over a positive is a positive. When you look at the second scenario, the run is always positive, but the rise is negative, and a negative over a positive is a negative. And we have discussed before about the fact that when you are dealing with lines, going uphill from left to right is a positive gradient. Going downhill from left to right is a negative gradient. So that means that we need to make sure that we consider, is the line uphill or downhill, meaning it's going to be negative or positive. Now, what if the line is vertical? And it doesn't matter if it's going up or down. If the line is vertical, that means we do have a rise because we go upwards or downwards, but we have no run because there's nowhere to go horizontally. So if there's no run, we look at our rise over our run, and because there's no run, that means we put in a value of 0 for the run, and anything over 0 is undefined. What about if we actually look at the horizontal line? Well, again, going from left to right, we could start playing with that, but we actually have no vertical climb. We do have a run, we have a horizontal movement, but there's no vertical climb, which means that the rise is 0, and when we start playing around with the rise is 0, and 0 over anything is actually equal to 0. So it's a case now of trying to summarise everything that we've looked at here. So we've got the gradient's equal to rise over run. If the line goes uphill from left to right, it has a positive gradient. If the line goes downhill from left to right, it has a negative gradient. If the line's horizontal, well, what did that mean? That meant there was a 0 gradient. And if the line was vertical, that meant the line was said to have an undefined gradient. So there's our 4 different scenarios that we need to know off by heart. Now, let's consider a graph where we've just got 2 points placed on a line, and those points have an x value and a y value, which the first point we'll call x1 and y1 because it's the x and y value of the first point. The second point we'll call x2 and y2 because they're the x and y values of the second point. What we can do is make sure we label those on our x and y axes respectively, and then we can notice that we can create a horizontal line. Now, what distance is that green horizontal line? What distance is it? Well, it's going to be the distance out to x2 minus the distance out to x1, which makes the green line have a length of x2 minus x1. Similarly, we can actually consider our vertical line. Now that's going to have a distance of y2 minus y1, because when you look at the vertical distance, there's your y2, there's your y1 height, and when you subtract them, that leaves you with the height that we're interested in, the y2 minus y1 height. Next, we have to consider how we can link those. So let's see how we can link them. What happens is we know that the gradient's equal to the rise over the run. But looking at our diagram, we know the rise and the run are now y2 take y1 over x2 take x1. So there's a link that allows us to use an algebraic formula. Remember, rise over run gets used if you've got a picture. You can figure that out easily. y2 take y1 on x2 take x1 is the formula you use if you want to just algebraically find the gradient. when you know 2 points and you really don't want to draw the diagram. Now, let's just review that. The horizontal distance is x2 take x1. The vertical distance is y2 take y1. Vertical and horizontal lines we know are at right angles to each other. So, we've got our two formulas that we've discussed. Let's introduce the angle theta. Now we know using trigonometry that the tan of angle theta, so we're using SOHCAHTOA now, the tan of angle theta is equal to the opposite side over the adjacent side, which means tan theta equals y2 take y1 over x2 take x1, because they're the opposite and adjacent sides. Now, let's just link this back to the formula that we already know. y2 take y1 on x2 take x1 is tan theta, but we know y2 take y1 on x2 take x1 is also m. Well, from there we can say m equals tan theta. So another way of describing the gradient is tan theta. But what's theta? Theta is the angle that the line makes with the positive side of the x-axis. And it's important that we remember that. It's always the angle that the line makes with the positive side of the x-axis. Now, let's just have a look at these two different diagrams that we've got drawn here. You can see in the first diagram that the line is going uphill from left to right. So we've got our line going uphill from left to right, and we've got our angle theta on the positive side of the x-axis. We can see in our second diagram that we're going downhill from left to right, and theta is still on the positive side of the x-axis. So, we need to make sure we're aware that theta is always on the positive side of the x-axis. Now, let's have a look at this example. We need to find the gradient of the line that's given. Now, it's important to choose points wisely. We want to choose points where we know the line is actually touching the grid, if you like, for the x and y axis. So, I could be choosing any points, but I believe those two would be the best ones to go because you can see they actually touch nicely the grid. So I can now draw my right angle triangle in, and I have a run equal to 1, 2, 3 units, and a rise, 2, 3, 4, a rise of 4 units. Now our formula we know is m equals the rise over the run, which in this case would equal 4 over 3. So our gradient is 4 over 3, or 1 1/3. We notice that the line is going uphill from left to right, which means the answer should be positive, which it is. Well, let's try finding the gradient of this line. Now notice this line goes downhill from left to right. There are several points I could choose for this one, and if I look at the question, I could choose this point, or this point, because they're all fairly easy to use. Doesn't matter which 2 points you use, but if you choose points closer together, you'll have less cancelling to do. So I'm going to choose to draw down and across. Now what's my rise? My rise is equal to, well, it's 1 unit. I could put -1 if I wanted to because I headed down 1 unit, but I'm not going to worry about that. My run is 2 units. So let's think about how we write this down now. The gradient equals the rise over the run, which equals 1 over 2, but I must put a minus sign in front because it's going downhill from left to right. So there's my gradient. Let's try example number 3. Find the gradient of the line passing through the point 2, -3 and 5, 9. Well, let's use our formula. I don't want to draw the graph. What I actually want to do is actually just use my algebraic formula. So m equals y2 minus y1 over x2 minus x1. That's the formula. Let's have a look at what my values are. Let's come over here. That's the x value of my first point and the y value of my first point. If I look at my second point, that's the x and y value of my second point, which means I can come back to my formula now. M is going to equal the y value of the second point, which is 9, minus the y value of the first point, which is minus 3, over the x value of the second point, which is 5, minus the x value of the first point, which is 2. So the gradient will equal 9 minus minus 3, which is the same as 9 plus 3, so I get 12 over 5 take 2 is 3, and 12 over 3 is 4. So the gradient of the line that passes through those 2 points is equal to 4. Let's move on to example number 4 now. Example 4. Prove that the points, well, we've got 3 points, and we need to prove that those 3 points are collinear. Now, what does the word collinear mean? Well, collinear means that all of my points lie on the same line. So I'm talking about the word collinear, that all the points lie on the same line. Well, I've got 3 points there, so what I'm going to do is I'm going to find the gradient of the line that joins the first 2 points together. So let's call that gradient 1. Now my formula is y2 minus y1 over x2 minus x1, which equals, now the y value of the second point, I'll look at the points in order, y value of the second point is 9, minus the y value of the first point there is minus 3. The x value of the second point, 5, minus the x value of the first point, 2, which becomes 9 plus 3, which is 12. 5 take 2, which is 3, which gives me a gradient of 4. Now what I'm going to do is I'm actually going to mix it up a little bit now. I'm going to consider something a little bit different. I'm going to consider the gradient between my second and third points. And I'll call that gradient 2. Gradient 2 equals y2 take y1 on x2 take x1, which equals the y value of my second point, 33, minus the y value of the first point, 9, over x value of the second point, 13, minus the x value of the first point, 5. 33 take away 9 is 24. 13 take away 5, we get 8. 8 goes into 24 3 times. Would you look at that? The two gradients are different answers, which means the points are not collinear. And that's a mistake from quite a while ago, because I meant to give an example where the points were collinear, but you can't prove these points are collinear because they are not. They're not collinear. Let's have a look at example number 5. Now, for example number 5, let's have a look at what's going on. Find the gradient of a line that makes an angle of 120 degrees with the x-axis in the positive direction. So, let's have a look at that and see what actually happens. We get a protractor put onto our picture so that we can actually measure 120 degrees. And remember, I'm always measuring from the positive side of the x-axis, which means I have to measure around this way, because that's the positive side of the x-axis. Let's see what we actually generate. If I actually measured an angle of 120 degrees, there's my line that I could draw in from the position that I have the protractor in. Let's remove the protractor now, and there's my 120 degree angle. Now, I don't actually have to go through the origin. That line could be actually positioned in a lot of different places, anywhere. It doesn't really matter, as long as the line's positioned along the x-axis in such a way that the positive side has an angle of 120 degrees. So now we can actually answer the question. We actually get our formula from earlier on, m is equal to tan theta. We also know that the angle's 120 degrees, so m equals tan of 120 degrees. And the tan of 120 degrees from earlier trigonometry is precisely the square root of 3 if we wanted the answer exactly, or we could say it's approximately minus 1.732. Notice the minus sign occurs because it's going downhill. Our line is travelling downhill from left to right. Well, that's the end of the class as such. It's now time for you to try and do some of the questions from exercise 7.3. Have fun.